it depends on the testing strategy that you're using, because we have fault-based models, and there is, like coverage-based models, this criteria-based models, so it depends.
So there are some approaches
yes.
for testing.
Yeah.
And so basically you have something that sort of, they use implicit fault modeling.
Yes. Yeah.
So in fact, I will point out that we talk about stuck at zero, stuck in fault models, and we will talk about coverage of stuck at zero and stuck at one false. And we will see that there is something analogous in software. You have a few different coverage measures, and higher coverage you get, that means your testing has been more thorough. But let's right now talk about hardware. Sort of presumed false, such that testing for them will test for most false and let's qualify that most false of a specific class. So the idea is that if you have a good fault model, if you test for all the modeled faults, you should have tested for all the possible types of defects that could arise. Now, to decide if a certain fault model is good or not, it takes a fair amount of research. So for example, if you wanted to verify the applicability stuck at zero, stuck at one fault modeling, you could simulate defects at a lower level, perhaps use SPICE and simulate defects at a low level. And find out what is the impact of those defects, shorts, opens, introduce some resistances. And you might find out that quite a few of them will actually show up as stuck at zero, stuck at one faults. Now they're used for test generation. Basically, you generate tests assuming that you have certain kinds of faults, and also used for fault simulation. So if you want to evaluate coverage, then you need to do fault simulation. So that will allow you to find out that if you apply this set of tests, what kind of coverage you would get. And a good fault model is going to hide the complexities of lower level actual defects, which you can have an infinite number of them. Now, how do people come up with fault models? They basically are based on past knowledge, past modeling experience. And of course, researchers, they keep looking at questions of fault modeling time to time. And in conferences, people will share what they have found. If you use a certain fault model, are you going to catch this new type of defect or not? Now let us look at some common fault models. Let's start here. Now here is one model, and that is no model. You simply test exhaustively. Let me get a bigger piece of chalk. You simply test exhaustively. But you apply all possible input combinations. Now, what do you think about this?
It's very expensive.
Too expensive? Certainly for software, because exhaustive testing for software would be practically infeasible. That's also true for very large hardware. However, you could have some hardware blocks that are sufficiently small. So for example, you have a block of hardware with 8 inputs, and if you have only 8 inputs, then 2 raised to 8, that is, how much is that?
256.
Uh, 256. So it's only 256 combinations. But then as the number of inputs increase, the number of combinations, they grow exponentially. So actually there is, people have come up with some approximations. So there are some people who have come up with pseudo-exhaustive testing. So sometimes a given thing can be partitioned into small blocks, and then each of the small blocks can be tested exhaustively. So sometimes some kind of exhaustive testing can be done, but in most situations for large hardware, pieces of hardware, or for software.
Is it the most effective testing?
Is it more effective?
Yeah, is it like, because if we cover all the possible inputs, then we're supposed
Now effectiveness is a relative term. So usually if you are using, so the question is this, for the same number of input, for the same number of tests, in other words, for the same amount of testing time, which approach is going to give you the best coverage? And usually exhaustive testing will not be the best choice. But in some cases, if it may be okay. If it is a small circuit, small combination block, you can apply all possible combinations. And that could be feasible. And there is some literature on pseudo-exhaustive testing, which I guess we are not going to do, but if you are interested, you will find the literature on it. Now let's look at some hardware fault models. Now I should mention that even for software, there is something like exhaustive testing. Sometimes the software input domain is partitioned, and the attempt is made to exhaustively test all the elements of the partition. But it's not quite exhaustive, because you make some assumptions there. And let's look at some gate level models. And there, we are going to look at stuck at 0 or 1, which is the most common, so we are going to look at it in some detail. And bridging faults and delay faults, they are also important. Delay faults are actually quite important for hardware, because delays cannot be precisely controlled in hardware. So delay faults are quite common, and testing for timing related defects is a very important challenge. And you have then, transistor level fault models. Now sometimes we will talk a little bit about software fault modeling. let me put a question mark there. Basically, there's something sort of similar, not exactly the same thing. Now in hardware, let's look at hardware. Now in hardware, you can have some temporary faults. So there are some defects that seem to come and go away. And sometimes it could be because of sensitivity to charged particles. So you have a memory and a charged particles. So everywhere we don't see them, but we have. The universe is full of charged particles. And these charged particles are always hitting your memory chip. Even if you encapsulate your memory chip, there would be charged particle coming off from the encapsulating material. So basically, part of nature. And it is possible to design memory chips with a certain amount of robustness relative to charged particles, but you can never control the problem completely. And in fact, problem has become a little severe recently because the device dimensions have become very small. Now, we are not going to talk about temporary faults for now. Later we will come back to them when we will look at reliability evaluation. But we are going to talk about permanent defects. Let's call these things failure mechanisms. So I think you have a few minutes, right?
2 minutes left.
2 minutes? Okay. That should be plenty. So some of the common things are opens and shorts in circuits. So basically things that are supposed to be connected, they are not connected, so the line is broken. Very common thing. And sometimes things that are not supposed to be connected, they get connected because some metal moves around. So two things that are adjacent on the same chip, may get connected. Or maybe during the soldering process, your board, the stuff is soldered on a board and two adjacent things, they get connected together. So these are the two most common of the failure mechanisms, opens and shorts. And if you will take a chip and magnify it, you can actually see some of these things. And then you can have imperfect devices. So you have, for example, excessive delays. Now these imperfect devices, they work, or they work most of the time, but occasionally they don't work. So we are going to next time talk about the classical stuck at 0-1 fault model, and we will look at some assumptions, and we will look at the transistor level fault models. And after having looked at the fault models, we are going to go to the next topic, which will be test generation. So we will continue with fault modeling for probably a couple of lectures. And so I will introduce the idea of how a certain fault could be tested. And later on we will come to test generation strategies. So look for that feedback module 1. Should be available sometime today on RAMCT. Everyone is able to access RAMCT?